how to build a simple machine learning quantum model. This is not my original idea. I took that from a paper that I'm working on. That's kind of like that I'm basically breaking down for the YouTube channel as well, which is how to build a quantum GAN, generative adversarial network. And I found this really interesting. So what do you wanna? It's a really basic idea. So I'm going to link the paper in the description below. But what do you need for a model to work kind of good enough? So you need to be able to train it so that it can learn, right? So this means it needs to be parameterized. So it needs to have some parameter that you can then read and actually adapt and improve. And with this, and it needs to be able to kind of move through all the different space of possible solutions, right? I think that's the idea. Is it needs to be able to give outcomes, like a wide range of outcomes, so that can represent your problem in really rough terms. I'm no machine learning expert, so don't take that too seriously, but that's the idea. So how can you do this with a quantum circuit? So you can do this with with a combination of two simple gates. So of rotation gates. So rotations. So RZ gates, right? For example, RZ gates, RX. So RX gates first, RZ gates. I'm not so sure if it really matters, and then control Z rotations. So this is a really simple way of doing that. And you see that each gate has a parameter, which is an angle. Now, how the way, how to justify that this really explores enough? Well, I mean, you can go two ways. So you can go one way, which is a typical, more mathematical or geometrical way of seeing things, which is the Bloch sphere. So you've got the Bloch sphere here, and basically you can see that you can move around the entire sphere by just rotating over the x-axis and the z-axis. So you can even implement y rotations just by combining those two. And the control rotation is to implement entanglement. I'm not gonna go into details here of what this is. You can check out the other videos in the channel. But entanglement is a property that so it's basically the correlations that you also want to be able to explore in your solution space, how those two qubits are correlated. And so you could ideally just pack all that into a subroutine, right? So you could say, so you could take that. So you could take that here and then pack it all into a subroutine called whatever, like model, right? And then like this, and then parameterize all that. Now, I think that doesn't fully work yet in this editor, and I probably could do maybe a code example, but we'll do this later probably. Just to stay really at the surface of this topic. So each of those could be a parameter, so it doesn't have to be, it doesn't have to be all the same. It actually should not be the same. And then you put in here so that's qubit 1. So I mean actually this would be 2 qubits in here. So you could do that and then basically go and place this in your circuit. But so to give you an example of what this looks like, let's just put here random numbers. Just random numbers. I don't know, just 1.2, 3.2, 4.3, 5. I don't know, just random numbers, right? So if I now take a look at the at this visualization, the density matrix, it's a really interesting visualization because that's kind of a graphical representation of, or you could use that as a visualization of your model. So this is how your model looks like. I mean, not only this, but also this one here. So you see that it has a real component and a complex component. That's the beauty of so that's the beauty of quantum computing when it comes to machine learning models, is that the space that you can use is immensely huge. It's just immense. So and this is just with 2 qubits. And then you can tweak, what you could do now is you could do a combination of a hybrid. So you could do like a combination of classical and quantum. And so if you go back to the code here, so if this is well parameterized, you could actually take the collection of those parameters and then find a way that is useful for your algorithm or your problem to just optimize that. So you can, you could try to find a metric or sort of tweak things and then see if that takes you where you want to, what you want to do. If you want a classification model, or if you want something else, then you basically can tweak those parameters, and that's kind of your learning. And this is just with 2 qubits. So imagine the power that this actually has. I mentioned that this the reason this explores all the space of possibilities, or almost all of it, is because of the Bloch sphere. But I'm also not super happy to use that as a basis explanation, because it's a bit mathematical, but it's okay, I guess. Another thing you could just, if you don't care about the Bloch sphere, I mean, if you play around with rotation gates, you will realize that they're called rotation gates because at some point when if you play with different values of their parameters, at some point you realize that they are cyclic, so they are just going back again and again, so they are kind of rotating, so to say. So they have a finite sort of a finite space that you can explore with each gate, but then when you combine them, you can do really cool things. You could actually grow that. You could make that even more, like if you want to add 4 qubits. And I think that what you then have to do, but I'm not so sure the paper explains that more in detail, is you kind of replicate the same structure. You do a control rotation on Z, and then I think you do another control rotation here, so you're kind of connecting the qubits, and this is pretty cool. I mean, you can also express those in terms of pi, so in terms of you don't have to put just numbers, but I mean, I don't know, something like that. And then if you go to the visualization, that looks really nice, and go to the density matrix, boom, that's just, you see the space off. So what you can explore here in terms of solution space is huge, right? So yeah, I hope that was useful, and I think that's one of the really interesting learnings that I've recently made.